Hello, class. This is my presentation about structural fires and structural fire failures. So, we're going to be talking about general fire safety, structural fire safety, the importance of fire resistance and what that means. Then, we're going to talk about codes, some apprehensions about new codes, the current application of the codes, and why it's so hard for us to shift from one type of model-based coding to a different type of code for our buildings. And lastly, we're going to talk about fire performance, which is basically an assessment of the way that materials, buildings, whatever, act during a fire. All right, so for some background, there's a problem, and this is why we need to address structural fires. This data is just from the year 2004. There were 1,550,000 fires, which resulted in 4,003 deaths. There were an additional 100,000 injuries, of which 80,000 were firefighters. There were 10 billion direct costs related to structural fires, and the total cost of structural fires surpassed $50 billion in the year 2004. And these numbers are not adjusted for inflation, so it's truly much higher. There have been a few fires throughout history that have kind of been eye-opening events that have led to reform and action in government. One of the first ones was the Great Fire of London. It lasted 5 days and spread rapidly with no containment. It burned 440 acres, 87 churches, and over 13,000 homes. And then in Chicago, I think we've all heard of it, the Great Chicago Fire. This occurred in 1871. It lasted only 3 days, from October 8th to October 10th. And during this time, the roads, everything was made out of wood. There was absolutely no code in place. People really didn't think that could happen. And when you put that together with now what we call Chicago the Windy City, you get a recipe for disaster. In 3 days, 17,000 buildings were destroyed, over 300 people were killed, and over 100,000 were left homeless. And if you want to do some research on it, there's a few interesting theories of how the Great Chicago Fire actually started, one of which was a farm helper knocked over a lamp or lantern inside of a farm that caught a hay bale on fire, and the fire spread uncontrollably from there. But there's a lot of weird theories. Nobody's certain on how it started. There's also a few more examples from recent history. 9/11 was a good example of the importance of structural engineering when it comes to fire resistance. As we all know, the buildings buckled under the weight of the stories that were above them. This was due to the materials that supported the building not being thermal resistant, which meant As the temperature greatly increased, their structural integrity greatly decreased. This is also similar to what happened during the Eurotunnel fire. That occurred when there was a fire inside of a tunnel. Basically, no thermal resistance was in place, and the entire tunnel had to be shut down and completely retrofitted with new materials, which ended up costing a lot more than it would have been to just build the tunnel with those um, thermal graded materials to begin with. A few more recent examples was the Oakland bridge collapse. This occurred when a semi hit a pole, started spewing gasoline everywhere, and it burned so hot that the concrete and metal supports of the bridge actually lost structural integrity due to the heat and buckled and collapsed. Same thing happened in Atlanta recently. This caused a gridlock for the entire city. Then, as you see, there's the wildfires that occurred recently in California just this year and a few years ago, and then the wildfire that occurred in Hawaii. And structural fires associated with wildfires are becoming more and more common because our structures are becoming closer and closer to wildfire prone areas, let's say, like forests, etc. We have so many more buildings now that they're spreading to areas that are more likely to experience forest fires. And then the Station nightclub fire occurred at a concert. Over 100 people were killed at a nightclub because of the lack of compliance to building codes, especially commercial building codes. And that actually led to a big reform in the different types of building codes that take place or take effect over commercial, residential, and other types of buildings. So performance-based codes are what the United States are ultimately looking to shift towards. They provide more flexibility, more situationally appropriate decision making. But some of the apprehensions are the lack of model data, there's a lack of testing, there's a lack of materials, and those materials themselves are expensive. There's a lack of resources, a lack of training, and a lack of monitoring and adherence, which basically means there's no compliance people going around checking on performance-based codes because they're a lot harder to check from a checklist perspective. If you're looking from a point of view of an overall picture of the building, performance-based code is very easily standardized. But if you're looking at each component of the building, then you fall back onto a prescriptive-based coding, which basically just gives you a very black and white idea of exactly what each component of your house has to do. It takes out all of the creativity, all of the problem solving, all of the future, I guess, excitement that comes with trying to come up with safer buildings. So a lot of people are pushing for this more performance-based code rather than sticking to the same old prescriptive-based code. Um, a few types of codes are the fire resistance ratings. This is basically a system that takes materials used in construction of buildings and it rates them to see how quickly they will catch fire in a fire-like situation. Um, the higher, the longer it takes, the higher your score is going to be. Then there's occupancy type codes. These codes are different for different kinds of buildings. Residential buildings are going to have different codes than commercial buildings, etc. Then there's construction codes. These codes tell construction companies what their protocols are to be whenever they're using heavy timber versus synthetic stuff. Basically, there's different policies that they have to put in place at construction sites and during construction projects that is going to be slightly different for whatever kind of material they're using. Fire performance, like I said, this is kind of a measurement of how each material is going to act when it comes to a fire. A few of the things we're looking for are a high temperature intolerance. That means that when something goes up in temperature, it degrades in quality, strength, what have you. We're next looking for toxicity. We're looking for how fast flames will spread. We're looking for the speed of the degradation of strength as the heat increases. And then we're also looking at cost because we have to walk a fine balance between affordability and mitigation. Few types of structures we look to protect are buildings, stadiums, any type of stadium or event location is going to be a higher priority because the population inside of these buildings are going to be surging at certain times. So obviously at that population surge time, there's going to be a higher risk for a major disaster. There's oil platforms, there's tents, for example, weddings, circuses, not as common anymore, but tents are very flammable, especially the tents that were not up to code. Then there's stages, there's towers, and then there's storage. That could be storage units, like somewhere, let's say I went to go put my furniture somewhere. This could also mean storage tanks where there's natural gases or oxygen being stored. All right, now let's jump into fire safety. Some general fire safety rules. You can't prevent all fires, so that's why we focus on mitigation to prevent any fire that does happen to not be as severe as it potentially could have been. So a few ways we do this: automatic sprinkler systems, automatic fire alarms for advanced fire detection. Then we also want to make sure that our escape routes are clearly labeled, especially in commercial settings. Fire-resistant barriers are good, especially in larger buildings like hospitals or schools. Having these barriers that can close off in each hallway, kind of forming an airlock for each hallway, and this can prevent the fire from spreading outside of that hallway and spreading into further rooms on higher or lower floors. All right, now So for structural fire safety, we have design requirements. Of course, engineers are going to be tasked with modeling things like the required width of a door for a commercial building versus a residential building. Commercial building is going to need a bigger width of their door because they're probably going to have more people inside that building at certain times. Then we look to prevent the loss of life as our main priority. We look to prevent the loss of property as well, but the loss of life is our main priority. One way we can do this is really diving into fire resistance. There's plenty examples of contractors, building owners, what have you, trying to cut the corners, shave some costs, and using, for example, non-flame resistant insulation. This was one of the problems at the nightclub fire that killed over 100 people. The building was fully involved in less than 10-15 minutes, and there was only one exit. And once the main stage area filled with smoke, it all happened so fast because there was no fire resistant materials used in that building. The concert goers stood no chance. Practicing evacuations is also a great practice. This will, even if the people that are there during the fire aren't there for the practice, your staff is going to be trained on how to lead an evacuation so that they will be able to lead during the event of an actual fire. Next thing we need to do is to control the spread. This goes back to what I was saying about hospitals and schools having fire barriers and fire doors in their hallways. Finding the fire in a bigger building and isolating it will go a long way in preventing loss of property and loss of life. Then, of course, we have building codes. That takes us back to the argument of prescriptive versus performance-based building codes. But as I said, we are leaning towards performance-based building codes because they allow for more adaptation, creativity, and innovation. So the goals of fire safety and structural fire engineering, protecting lives. We also want to make sure that the mission continuity is in place. We don't want to just push real hard and then forget about it. This needs to be something that is continuously adapted, like everything else in disaster management. The cyclical nature of any kind of management strives for continuous improvement. And then lastly, we want to look for sustainability, which means training, compliance officers that actually make sure that the building codes are being followed, and then affordability. We want to make sure that the building codes put in place are affordable enough that most contractors will be willing to do it. Thank you for listening, and here is a list of the sources that I used.